Hello everyone. In this video, we are going to discuss about the control groups in Docker and their uses. We know that in Linux when we start containers, these containers will run as processes in Linux host. So these processes consume resources like CPU, memory, network resources, disk IO and so on. So these resources are limited to all the processes. So there should be a functionality to limit the resources which are used by multiple containers within the host. So in Linux we have a concept called cgroups. So cgroups is a feature to control how much resources a process can use. So in case of Docker, it will use the cgroups feature to limit the resources for each of the containers. So it enforces the limits on all these resources. Since the resources which are used by the containers are limited, it will help us to work against the DOS attacks, for example fork bombs. So in this video we will also see how it works against these fork bombs. Now let us see in detail about these cgroups with the demo. This is a Linux virtual machine. Let us check all the processes which are running on this machine. So these are all the processes with corresponding process IDs. Generally when the processes are created, the control groups are created to manage the resources which are required by all these processes. So in which directory the control groups are created? We have sysfs. Under this, we have a directory called cgroup. Let us go inside this directory. Here we can see that these are all the subsystems corresponding to the cgroup. Here the subsystem represents a single resource like CPU, memory, block IO devices and so on. So we have different hierarchies of cgroups which are attached to each of these subsystems. For example, let us go inside one of these subsystems like CPU. So here we can see various options for the cgroup like CPU shares, CPU stats and so on. And also here we can see the cgroup procs. Let us open that file. So these are all the tree of PIDs which are attached to this CPU subsystem. So let us check the files again. These are the attributes through which the access to this CPU resource will be limited for all these process IDs. That means we can change the CPU shares or CFS quota and so on for different processes which are attached to this CPU resource. Similar to CPU subsystem or resource, for other subsystems also, we will have the file cgroup.procs. So let us verify the same. Here we can use the find command. Here we can see that for each subsystem like memory, devices, PIDs and so on, each contain the cgroup.procs file. So each file will contain corresponding tree of PIDs which will be attached to corresponding subsystem like PIDs, memory and so on. Now in case of Docker, when we create Docker container, we'll have a separate directory here with the name Docker. So that Docker will contain corresponding container ID. So now let us try to create two containers using Tomcat image. Here I am giving the name as D1 for the container 1 and we are using the Tomcat image. So a container is created. Similarly, let us create another container T2. So now we have two containers. So after the containers are created, let us go inside CPU directory now. So here we can see that a new directory Docker is created. So let us go inside that. So inside Docker, we have two containers. So let us go inside one of these container IDs. So this container ID also contains all the files which were discussed earlier. So let us verify the cgroup procs here. So this is the process ID of the container process for which all the CPU resources are limited. We can verify the process here. So this process indicates the Tomcat process within the container T1. So for this process ID, the resource usage of CPU is limited and which can be controlled via various attributes like shares, CFS quota and so on. So similar to this container, we can also see similar files for other container as well. Similar to CPU subsystem, We can also go to memory subsystem to see the directories corresponding to these two Docker containers. So let us go inside memory now. So here these are all the attributes corresponding to this memory subsystem. Here we can see the Docker directory. Here also we have two directories for the Docker containers. We can go to any of these containers. So these are all the files which contain the attributes through which the assigning of this memory resource to this container can be controlled. Now let us perform some of the cgroup operations using Docker commands. Let us start with memory. By default, all the memory which is present in the machine can be used by containers, but this can be controlled using the limits. So for example, here let us create a new container T3 and assign some memory limit for that container. So here I am assigning memory and I am assigning 300 megabytes, and we are using Tomcat image here. So now we have created new container. Now let us see the containers in this machine. So we have 3 containers here. We can verify more details about these containers using docker stats command. Here we can use multiple options. I will use this no stream option, which will disable the streaming stats and it will only show the first result. So we can see the memory available here in this machine. Here we have 990 MB. So that means the limit for the containers T1 and T3 is 991 MB. But for container T3 we have set up a limit of 300 MB. So that is why here it is showing the limit as 300 MB. So this container can use the limit up to 300 MB within this machine. So if it crosses this limit, then out of memory errors will be thrown and corresponding container will be killed. We can also see without no stream option for the stats command. In this case, we can see continuous usage of memory or other parameters like CPU and so on. So let us close this. So now let us discuss about the CPU limit. For CPU also we have various attributes we can change. So let me stop 2 containers here, T1 and T2, and we'll try to create 2 more containers, T4 and T5. Now let us create T4 and T5 with CPU limits. So for CPU option, let us start with CPU shares here. So by default, this is the value for CPU shares. So we can assign value to the containers or processes relative to this value. For example, if one container allocated 768 and another container allocated like 524, the container with value 768 will get more CPU cycle when compared to another container with 524. So let us do that. So here I will mention the CPU share like 768. So here we have assigned CPU share 768 for container T4. Similarly, let us create T5 with CPU shares 524. So now let us verify the docker stats command. Now let us execute docker stats command. So this command shows the CPU utilization for containers T4 and T5. So this does not indicate the CPU allocation. This is the CPU utilization with the allocated limit for both the containers. To see how many CPU shares are allocated, we can execute docker inspect command. So let us do that. So we are inspecting T4 and grep it for CPU. Here we can see that the CPU shares are 768 and for T5 this is 524. So these values are relative to 1024. So the CPU allocation also will be done in the same ratio, like more CPU allocation will be done for T4 and less CPU allocation will be done to T5. This CPU shares is a soft limit. This is not a hard limit. This means that whenever some containers are free and they are not using the CPU, other containers can use the available CPU in the host machine. In addition to soft limits, we also have hard limits. Now let us discuss about the hard limits. For hard limits, we can use the CPU quota and CPU period. So before writing the commands, let us understand these parameters. The CPU period is the CPU cycle period that will be used by all the containers. The CPU quota is the amount of this period that will be used by each of the containers. Here in this case, we have 100 milliseconds for the CPU period, out of which we have assigned 50 milliseconds for a container through CPU quota. That means it will get half of the CPU cycle, and if we specify 25 milliseconds, then it will get 1/4 of the CPU period for every CPU cycle. So this way we can specify the combination of the CPU period and CPU quota for each of the containers. When we specify this quota and period, these are the values for all the combinations of CPU. For example, if you have like 4 CPUs and if you want to allocate half of the CPU cycle for the container for every CPU, then we have to assign the value 4 multiplied by this value. So now let us write some commands. Here we can check the default value of this period. So this is 100 milliseconds, and also let us check the CPU quota. The default value is -1, which indicates all the CPU period can be utilized by the containers if it is available. So before writing the commands, I am stopping the previous containers. And let us create new containers now. So I am giving the default value for CPU period. Here for CPU period, we are assigning 100 milliseconds, and for CPU quota, we are assigning 50 milliseconds for container T6. Similarly, let us create one more container T7. Here I will specify 25 milliseconds for T7. Now T6 and T7 are created with corresponding CPU quotas. We can verify the same values using docker inspect command. So here I am graphing for CPU. Here we can see that the CPU quota which is allocated is 50 milliseconds. Similarly for T7, it is 25 milliseconds. So in this ratio, the CPU allocation will be done for both the containers. That means T6 will be allocated half of the CPU, while T7 will be allocated 1/4 of the CPU, because the CPU period is 100 milliseconds. In addition to individual allocation of the CPU quota and CPU period, we can combine together with CPU's attribute. So let us create a new container with that. Here I am providing 0.2. That means 2 by 10th or 1/5 of the CPU allocation will be done for this container. Similarly, let us create another container T9. In this case, I will allocate 0.1. That means 1/10 of CPU allocation will be done for this container. So let us verify these allocations using docker inspect command. So here we can see there is a parameter called nano CPUs, which is the multiplication of this 0.2 into 100 milliseconds, which indicates 0.2 into 100 into 10 power 6. Similarly for T9, so this value obtained by multiplying 0.1 into 100 milliseconds, which indicates 0.1 into 100 into 10 power 6 nano CPUs. So in this way we can limit the CPU resources for different containers in Docker by specifying hard and soft limits. So now let me clean some of these containers. Now let us discuss about an important denial of service attack in which a process will replicate itself to create multiple PIDs which eats all the resources of the system. This is the Wikipedia page of fork bomb. So here we can see that we fork a process, and that process will call the same fork, and each fork will create a PID. So that means a process is replicating itself and it will create infinite number of PIDs. Finally, it will eat all the system resources, and that will cause the crashing of the system. In Docker also, if we create a container, within the container, if the process forks itself, then it will cause multiple PIDs to be created and it will eat all the resources of the host machine. To avoid that, we have to use the PID cgroup to control the limit of PIDs assigned to a particular container. So to explain this, let us use an Ubuntu image for creating the container. So here we are not assigning any PIDs limit. So now we are within the container. Let us try to create that fork bomb, what we discussed. So generally in the Unix shell, if we give this command, automatically it will create multiple forks of the processes and it will create infinite number of PIDs. It is like this is a function, and within the function it is calling the same function and assigning that output to a function. So here the fork is a function and we are calling the fork function here, and within the fork function we are calling the same fork function and we are sending the output to fork and we are running the command inside the background. So this will create a PID, and since it is calling the same function again and again, an infinite number of PIDs will be created. So in the Unix shell, let us try to provide this command, which will eventually create infinite number of PIDs. So after providing this, I am not able to type anything. So after this command, I am not able to connect to even that server because it will eat all the resources within the host machine. So let me kill this process and don't try to execute this command within your machines. So I have shut down that machine and again I will recreate now. Now I have restarted the machine. So let me connect to the same machine now. Now I reconnect to the server and I am restarting the Docker. So Docker is restarted. Now again let us create another container, but this time we'll assign the PIDs limit to that container. For this, let me create a container T9. And here let us assign PIDs limit. For this example, I am giving as 10. So now we are within the container. Let me run bash here. So again let me execute this command. So here we can see that, so since we assigned the limit, after certain forks it is saying that the resource temporarily unavailable because we have assigned a limit. So that means it cannot create new forks after that limit is reached. That means we are safe from this fork bomb denial of service attack. Let me close and come out of this container now. Now we can see there is no container T9. So this way we can prevent an important fork bomb denial of service attack by using the PIDs control group by sending a PIDs limit option when the container is created. In this video, we have seen the control groups in Docker and we have considered various examples like CPU, memory and PIDs and so on. We also have seen how these control groups can be used to limit the resources for each of the containers. I hope this video helps. Thanks a lot for watching.